Hey guys, welcome to the channel. Today we're going to be doing another Matlab video. So it's probably going to be a really long and boring video. But it's necessary because I haven't done any more research since our last video. So we're going to start with the RTL SDR again. And the antenna that's hooked up to, and I'm going to go ahead and plug that in. So that's hooked up. So last video, I showed you how to scan using Matlab for frequencies. And today I think we're going to continue on in the book, and I want to go into another chapter. So I want to work through a chapter today, so that's probably what I'll be doing. So I'm looking through the book right now. So if you want, you can go ahead and open up the book if you have it digitally. The last chapter we went through was chapter 3. I want to go over the modulation chapter, so I'm trying to look for that one. I think it was chapter 11, but I'm not sure. Okay, no, it's chapter 9. It's page 329 if you have the regular book. So that's what I'm going to turn to, 329. Well, that's FM, so that's frequency modulation. So that's wrong. We need to be chapter 8. Desktop AM transmission and reception, because I think ours deals more with amplitude modulation. I don't think ours has to do with frequency modulation. Okay, that's wrong too. That's more advanced. So we're looking at chapter 6. So it says amplitude modulation, AM theory, and simulation. So let's go to page 203. Sorry, it takes a minute when you're dealing with what we deal with. Okay, it says in this chapter, we will review extensively about classic AM amplitude modulation. The theory behind conventional forms of amplitude modulation will be presented, and there will be an opportunity to run simulations that demonstrate some of the different types of AM modulator. And then we will review various demodulators that will later be constructed in chapter 8 in RTL SDR AM receivers. So this is what I think they're using on us as amplitude modulation when they are able to encode it in the amplitude. But so I want to be able to decode their modulation, and I'm not sure what they're using, but I'm thinking it's amplitude modulation. Okay. AM is intuitively the simplest modulation method, and as will be shown later in chapter 11, it also forms the basis of many digital modulation schemes. In the most basic form, it is simply the process of mixing or heterodyning an information signal with a carrier wave to produce a signal that has two sideband components in the frequency domain. This process is called double sideband AM DSB modulation. Two variations of AM DSB transmitted carrier, AM DSB transmitted carrier, and suppressed carrier, AM DSB suppressed carrier. Further types of AM include single sideband and vestigial sideband. It says, in the following sections, we'll discuss and give examples of each of these in turn. Okay. Okay, so it goes on to give you the mathematical formula for, it says here an information signal is mixed with a carrier wave to produce the AM signal. And then it shows the mathematical formula for that. Let me see if I can pull up the digital book. That way I'm not looking down the whole time. Sorry. Oh, I downloaded it. That's right. I'm going to the website like it's on the website. I forgot I downloaded it. Okay. Okay, I'm going to share my screen so you can see what I'm looking at. Okay, let me close Zoom. Okay, so we're on 6, amplitude modulation. Hold on. Okay, so see at the bottom of this page, 207, that's the formula for the amplitude modulation. Okay. Okay, and it gives you the diagram right here, the block diagram. So this is how it mixes the signal. So the symbol in the middle with the X, the circle around it, that's just a symbol for mixer. So the signal goes into the mixer, and then the carrier wave also goes into the mixer. And then the amplitude modulated signal is the output. Okay. And they go into the math. Okay. Here it gives you more diagrams of it. So the magnitude, it says the baseband signal is a sum of sinusoids. And it says the carrier signal is the pure sine wave at a much higher frequency. And the modulated signal has 2 frequency components, an upper sideband and a lower sideband. Okay, so that would be like when I'm looking at something on there, it'd be this and this, like those would be, and this would be the carrier. So those would be the sine waves, but Okay. So this is just giving you a diagram of 3 signals and how they're outputted to be one signal combined. So you've got the amplitude of the first signal, the amplitude of the second signal, and the amplitude of the third signal, and they combine to make this one signal. And it's talking about the mixing the baseband signal with the carrier and how that math is. And it goes into more math. I'm skipping. Okay. It says next in exercise 6.1, a simple Simulink simulation will confirm via simulation what happens to the sinusoid signals in the time and frequency domains as they are modulated onto a carrier to produce an AM DSB SC signal. I forgot what that means already. They're blanking me. Suppressed carrier. Okay. So amplitude modulated, double sideband, suppressed carrier signal. Okay. Okay, so the blue peak right here is information signal. And these are the suppressed signals, the 2 green spikes. And the orange one is the carrier wave. The information signal is a single tone with a frequency of 2 kilohertz. The carrier, also a single tone, has a frequency of 15 kilohertz. When these are mixed together, the AM DSB SC signal is generated. You should see from the spectrum analyzer that the modulated signal only contains 2 frequency components, located at 13 kilohertz and 17 kilohertz. It is clear there is no carrier present in this signal as there is no green component at the frequency carrier. I just skipped a page, that's why it's messing me up. I hate the way this scrolls. uh, okay. The red dashed line overlaid on the time domain plot of the amplitude digital sideband suppressed carrier signal shows how the information signal has affected the amplitude of the carrier. As suppressed carrier modulation has been performed, the modulation index of the signal is greater than 100%, which means the no information envelope is present. We will discuss further in section 6.3. I think I have that wrong. I can't ever remember those. Oh, that's right. Okay. Okay. While amplitude, digital sideband, suppressed carrier signals are simple to generate and understand mathematically, radio receivers require relatively sophisticated coherent demodulators in order to extract any information from them, due to their lack of an information envelope. Amplitude modulated digital sideband, double sideband, sorry. Transmitted carrier is an alternative amplitude modulation scheme that enables us of non-coherent demodulators. Here, an information signal input transmitted with a DC offset amplitude output is mixed with a carrier wave signal carrier transmitted to produce the AM signal amplitude modulated double sideband transmitted signal. Okay. The block diagram for this modulator is shown in figure 6.6. So the transmitted signal goes in and it's added to amplitude modulation output, and that goes in the mixer. Along with the carrier wave that's transmitted. And then the output is an amplitude modulated double sideband transmitted carrier. Okay. There's the math. The maximum value of the modulation index can take whilst keeping the envelope intact is 1 or 100% as shown in the figure. Okay, so it's showing you 3 figures. So the orange dots are the information, how the information is encoded. So this has a modulation index of 0.5. So that would be the difference in amplitude that they're measuring. So that one would have that type of encoding. Next one would have an index of 1, which they say is the maximum information envelope. Then they're saying if it is above 1, then the information envelope is destroyed. And that's what they're showing you here. So then I guess they can, I don't know how that would work. I guess it'd be too much noise, so they wouldn't be able to process it. I don't know. I need to sneeze, I'm sorry. Ooh, sorry, I had to mute. Okay, me throw that away. It's just so complex. If you're not like a signals person, it's just so complex. It's just okay, where were we? I lost my page again, didn't I? Finally, the exercise, maybe. No, I think I skipped the exercise actually. Okay, here it is. So maybe we can actually work in Matlab and figure it out. Okay, open Matlab, set the working directory to the appropriate folder so you can open this model. So I'm going to minimize that. Let me close out of that. I'm going to try to do this so I can have both screens. Okay, so working directory to AM simulation, AM DSP. So I'm going to go to open Matlab. That's not it. It's in downloads. It's in the folder. Then AM. Then simulation. AM. This is a suppress carrier one. Did it open? Um, it's wanting me to add that folder because it doesn't know how to get to that folder. That's what that means is add to path. Yeah. Let's add it. So it's in downloads and then it's this folder. So we'll just select that whole folder and add it to its path so it doesn't freak out. It's trying to pull files from that folder. Okay, you can close that now. Sorry, they're hitting my voice. I don't know how they do that, but they do. Okay, once you have set that path, update the block diagram. Update. Okay. Okay, so I'm going to open that again. Open. And then I'm going to go back to downloads. And it said simulation. And there we go. Okay. Oh no. I was watching that earlier, sorry. Okay, here's the block diagram. 10 years later. This is the graphical interface. Let's see what it says. Okay, it should look like this. First information signal is the top. It's a single tone. The other is a sum of tones. They are input to the product block where they are mixed with the carrier wave to create the amplitude double sideband suppressed carrier signal. The information signal selector switch allows you to switch between them. To change the selection, simply click on it. Click, that part of your mouse on it. Leave this set on single tone for now. Okay. Oh, I hear thunder. Run the simulation. Begin the simulation by 1, run button in the Simulink toolbar. The 2 scope windows should appear. Position these two so that you can see both of them. Information signal is blue. The carrier is orange. AM double sideband signal suppressed carrier is green as shown in the legends. Okay, so let's run it. No, it's still saying failed to load library. Why is it saying that? It's running the other one. I guess I'll have to figure that out because it's not letting me do it. I thought it was going to tell you how to run. How to run from the SDR. But it does go through the 3 types of modulation for amplitude modulation, I guess. So it's good to learn that. I really want to learn how to demodulate a signal that you input into Matlab. So I'm probably going to look into that next. So but this is a good introductory to modulations and modulation theory. It just takes a really long time to go through it all. Well, we're running the signal sweep anyway. I'll have to fix how it adds that folder because it's not working. I don't think we really need it anyway because I think it's just a simulation and it's not really the application that I wanted. But now that I know that this book doesn't have that, that's a good. It's good to know. I don't know if this book teaches you how to demodulate or not. I think it does. I think I'm looking at chapter 7, and if we continue on, then that's what it goes into. So we might have to do that in the next video. These videos are probably really boring, but they're really necessary for me to be able to research, because if I'm not trying to study with you guys, then usually it gets suppressed and I'm not really able to get a lot done. So it really helps me too. So hopefully at least this is inspiration for you to do research in this area too. So that's really what we need. So that's the signals. So you can see the peaks in this, like if you follow the amplitude in this, you can see, like it looks like, I mean, to me, it looks like it could be amplitude modulation. There's a lot of uh, harmonics right there. Looks like we have a C wave, triangle wave. I don't know. Usually you can tell the shape of the waveform by the harmonics or the like, so this big wave would be a fundamental, and then it'd have harmonics off of it. So it would continue on, like you'd see peaks after it that would be like the same signal, but it's emitting noise. So that's what they call harmonics. And depending on like if those are even or odd, then you can tell the waveform. It's really interesting to study. Anyway, I guess I'll stop there. That was a good intro to modulation theory. Hopefully next time we'll have more actionable work. I'll have to study some more and see if I can get uh maybe an example signal to demodulate. That's really what I want to get, so we can see how it's demodulated. Anyway, I hope this helps. Bye, guys.